Thank you, Alessandro, for your presentation. So we now move ahead with the following talk, which is from Paolo. So, Paolo, I leave the stage to you.
Thank you, Davide. Hello, everyone. I'm Paolo Galfano, and today I will present you Unleashing Versal Systems for 3D Image Transformation. But first, a few words about myself. I'm a computer science and engineering student here at Politecnico di Milano, and my studies and research interests mostly cover computer architectures, FPGA, and computer graphics. In this project, I've developed an accelerator to accelerate 3D rigid image transformation, which basically consists in translating and rotating a 3D volume while preserving lines, parallelism, and angles. Among the many applications for transformation, registration stands out. 3D image registration is an image processing technique which consists in indeed translating and rotating a 3D volume to align it as best as possible to another reference one. It is applied in many fields, but here I focused on the medical field, in which it is used for robotic surgery, for example, and medical image analysis. And in this field, in the medical field, it's crucial to do it with high accuracy, high energy efficiency, and with low execution time. To achieve registration, a registration algorithm performs iteratively these three steps. First, it determines the parameters of the transformation using some research algorithm. Then it actually performs the transformation, and finally it computes a similarity metric, which is useful to assess the quality of the alignment. If, as the alignment is not good enough, these three steps are repeated over and over until the two volumes are aligned correctly. Now, this process has a problem. The transformation and similarity metric computation steps are highly computationally intensive. Indeed, literature has proven that they are the bottleneck of registration. Indeed, the aim is to develop a solution, an accelerator, that can achieve low execution time and high energy efficiency. But of course, this is also the aim of many other works in the state of the art. Regarding similarity metric, FPGAs have been proven to be the best solution to accelerate it, as they can achieve high speed and high energy efficiency. But for transformation, things are different. They are best accelerated with GPUs. Indeed, some software libraries like Cornea, MATLAB, and OpenCV support also GPU acceleration, but GPUs are too power hungry. So there are also FPGA-based solutions, which instead have a good energy efficiency, but they have unsatisfactory performance for the medical domain. So we have that the transformation is that part of the computation that still needs to be tackled, as it suffers from the trade-off between performance and energy efficiency. For this reason, we would like to have a solution that merges the benefits of SIMD architectures like GPUs, that is high performance, and also the benefits of FPGAs, that is high energy efficiency. But if we wanted to do so with one single device, one single board, there was no way to do it before 2019, as there was no single board which mounted both a SIMD and an FPGA directly interconnected. Then Xilinx in 2019, which now is AMD, released the Versal, which is an adaptive compute acceleration platform that has two general purpose processors. It has the FPGA and the AI engines, which are an array of 400 belief processors with vector unit, which makes them a SIMD architecture. And it is indeed by exploiting this heterogeneity, which have developed a framework that accelerates 3D rigid image transformation by devising a methodology that integrates the FPGA and AI engines to exploit the heterogeneity. This framework is also pluggable into an existing state-of-the-art similarity metric FPGA-based accelerator, thus proving itself in the task target of image registration. One of the main challenges and main contribution of this project was to map the computation on the hardware substrate. That is, use the FPGA and AI engines to do what they do best. Before seeing the mapping, let's first analyze the structure of the computation. we have two macro stages. First, a geometric transformation step in which, given some parameters and a set of coordinates, the transformation is applied. And then in the fetching stage, the transformed coordinates are used to locate in memory a pixel and then read it. So this is how the computation has been mapped. We have the compute-intensive part, the geometric transformation, which is done on the AI engine. And then we have the memory-intensive part, which is the fetching, which is done by a fetcher kernel implemented with an FPGA. Now let's focus on the fetcher kernel, which is the component with the most constraints and limitations. Indeed, a big constraint we have in this project, which is that the output must be generated in a deterministic and sequential order. But as transformation is a procedure that moves pixels around, requiring that it generates a sequential output means having to read the volume from memory following a random pattern. But random accesses in memory limit performances. This is because if we want to read 1 pixel at a time, we have to perform one read request for each pixel. And we have a latency between a read request and the time when the data actually arrives. If instead we perform sequential reads, we can group together multiple pixels and perform one single request for all of them. This is called burst, and it's implemented by the AXI protocol. Moreover, if we perform sequential reads, we can also further group pixels together and read them in parallel, thus widening the bit width of the reads, further decreasing the latency and increasing the reading throughput. But to do so, we have to use a specific data layout, which allows to read sequentially. This is a depth major layout, in which pixels along the depth dimension are stored sequentially in memory. This layout allows to exploit the burst and by bit width widening to increase as much as possible the reading throughput. Now we have seen the fetcher. Let's now see the geometric transformation, which is implemented in the AI engine. Programming the AI engines means dealing with statically scheduled compiled code, which actually requires the programmer to be extra careful in ordering the operations of the algorithm, so that because the order highly impacts the performance of the algorithm. Moreover, AI engines are memory constrained, so the programmer must be, again, extra careful in how we stores data in the AI engine local memory, so not to saturate it. And also, the program size, or let's say the memory which is dedicated to a program, is very limited. So the operations chosen for the algorithm must be chosen in such a way that the program size fits in memory. But the AI engine has a vector unit, which is that component which allows it to execute operations on multiple data at once. Exploiting the vector unit, I've developed the geometric transformation algorithm, in which first we select a chunk of 32 coordinates. 32 is the maximum amount of data on which the AI engine can perform operations. Then on these 32 coordinates, I perform the transformation using floating point operations. Then from the transformed coordinates, I derive the indexes. An index is what basically says the fetcher where to locate the pixel in memory. Finally, as some index may refer to pixels outside of the volume boundary, we have to filter out those indexes. And this is done in the last step before passing these indexes in output. Now we have seen also the geometric transformation, so the whole design has been covered. Let's see how it performs. I've used a dataset which is pretty standard in the medical domain, and I've measured the execution time and energy efficiency. The introduction of the new data layout brings a speedup of 21.6 times thanks to the AXI burst. But we have to consider that only changing the data layout, introducing it without implementing actually the burst, it already brings a speedup of 10.5 times. This is thanks to design choices that needs to be made to support the data layout, which already bring a noticeable speedup. Moreover, the design can be scaled. That is, the number of bytes which are read in parallel can be increased. Indeed, the best performing configuration is the one where 128 bytes are read all at once. And it achieves a performance of execution time of 7 milliseconds with a speed up with respect to the version, the single byte version of 46.1 times. We have to consider that the best performing configuration is not suitable for the state-of-the-art FPGA framework for the similarity metric. Indeed, the 16-byte version is the one that can be used for it, which has still a good performance of 22 milliseconds for the transformation. Comparing the best performing configuration for the transformation against the state-of-the-art framework Cornea on high-end hardware, that is the NVIDIA A100 and A5000, this framework achieves a speedup of 127 times with an energy efficiency improvement of 322. Moreover, considering the target task of image registration, the configuration which is a bit worse performing, the 16-byte one, again against Cornea on the same GPU, it achieves a speedup of 42.2 and an energy efficiency improvement of 116.9. This proves that this design actually does merge the benefits of FPGAs and AI engines by beating state-of-the-art in both transformation alone and an image registration step, both on high-end GPUs and FPGA. In the future, there are many things, many ways in which the design can be expanded, for example, by validating it with, within an entire registration procedure. But also, we can extend it to apply it on other domains. For example, if you work in automotive or you do computer vision or robotics, transformation is probably a very important task for you. So accelerated using a framework like this may be very helpful. Or again, in automotive or machine learning or robotics, or even if you work in embedded systems, having solutions which have both high energy efficiency and high good performances is crucial. So in general, heterogeneous systems may be what you are looking for. So I'm open to collaboration. So if you want, drop me an email and I'm happy to collaborate. Thank you.
Paolo, I have a question for you, which is about the execution time that you showed us that does not decrease when moving from 128 bytes to 156 bytes of for writing.
Okay, so you
explain a little bit more why this.
I guess you're talking about this this graph.
Exactly.
So we have that while scaling the bit width, we have that the reading speed increases so much that the application might arrive to be no longer memory bound, but compute bound. Moreover, there are limitations that are related to the bus and to the memory banks. So further study may help determine if it is feasible and even useful to maybe parallelize the computation so that the design becomes no longer compute bound.
So thank you, Paolo, for your presentation.